Welcome to my projectbazaar.com. Let us discuss about the novel 16 QAM and 64 QAM near-complementary sequences with low PM-EPR in OFDM systems. Let us discuss about the abstract of the product. So, as an attractive physical layer technology for wireless communication, orthogonal frequency division multiplexing has been applied in many wireless communication standards due to its considerable high spectrum efficiency, high power efficiency, multi-path delay spread tolerance, and immunity to the frequency selective fading channels. So, however, we propose a novel construction of 64 quadrature amplitude modulation, that is a QAM, near complementary sequences with low power peak to mean power envelope power ratio, that is a PM-EPR, in orthogonal frequency division multiplexing systems. So the proposed 16 QAM near complementary sequences can be constructed by utilizing a novel nonlinear offsets where the length of the sequence is n is equal to 2 power m. So the family size of the newly constructed 16 QAM nearest complementary sequences is 8 into m factorial divided by 2 into 4 power m plus 1, and the PM-EPR of these sequences is proven to satisfy. So the PM-EPR less than or equal to 2.4, as a proposed construction can generate a number of 16 QAM near complementary sequences with low PM-EPR. So the resulting is improvement of the code rate in the OFDM systems. So furthermore, we also propose a novel construction of 64 QAM near complementary sequences with low PM-EPR, which is the first proven constructions of the 64 QAM near complementary sequences. So the PM-EPR has the two types of the proposed 64 QAM near complementary sequences are proven to satisfy that PM-EPR is less than or equal to 3.62 or the PM-EPR less than or equal to 2.48 respectively. So the family size of the newly constructed 64 QAM near complementary sequences is 64 into m factorial divided by 2 into 4 power of m plus 1. Let us discuss about the flow diagram of the process. First of all, this is the overall flow diagram process. So this is the transmission model, and then channel, and then this is the receiver model. So this is generally simple OFDM block. So we're getting an input data. So in the input data, we're getting randomly to getting the input data, and then the modulation is a QAM modulation, that is a 16-bit QAM modulation. They are complementary sequences. So that is the process, and then we're converting into serial to parallel and the partition into subblocks. Subblock is divided into n point IF of t, that is the inverse Fourier transform of the process. Again, the converting into parallel to serial and partition into the subblock. So these are the blocks in the transmission side model. And then the channel, we using a AWGN Rayleigh fading channel. So the AWGN is a additive white Gaussian noise process, and then we're getting on the receiver model 16-bit QAM demodulation near complementary sequences, and finally we get the output to the PM-EPR is a reduction of this output. So in this paper, we propose a novel construction of 16 QAM near complementary sequences to enlarge the family size of the 16 QAM near complementary sequences. So the family size of the newly constructed 16 QAM near complementary sequences is 8 into m factorial divided by 2 into 4 power of m plus 1. So moreover, the proposed 16 QAM near complementary sequences satisfies that PM-EPR is less than or equal to 2.4, which means a significant PM-EPR reduction in the OFDM systems. Finally, our performance analysis is the PM-EPR reduction in the OFDM system. That is how we finally are getting the output. So furthermore, the satisfies the paper is a PM-EPR is less than or equal to 3.62 or otherwise 2.48. So the 16.4 QAM near complementary sequences is 64 into m factorial divided by 2 into 4 power m plus 1. The same process is again. Finally, we're getting the output, the PM-EPR reduction in the OFDM system. So these are the overall flow diagram of the process. Let us discuss about the running procedure for the product. So click the main file and then run. So there are many outputs are displayed. So these all the outputs related to our flow diagram. So this process is for example, this is a transmission model, and then channel, and we get the receiver model. So that is a process and getting the output also. So in this first figure, this is the first figure. This first figure, this is the input data. So the input data is generated randomly. So this is the input data of the process. So this is the first figure of the source. And then this is the encoding of the data, and the encoding of the data in the process of in the transmission model side. So these are the encoding of the data. So this figure is shown is the IF of the data. Again, already we know that the flow diagram. So n IF of the data is inverse Fourier transform. So this figure is shown that the IF of the data process in the transmission side model. So in this figure we describe the cyclic prefix insertion, that is a CP insertion. So this process also in the transmission side model we getting the output of the IR50 and then we get the cyclic prefixes of the data. So this is the x-axis and this is the y-axis. CP insertion is basically needed so because of the low complexity of the system. So in this figure shown that the AWGN channel noise, so that is a noisy signal. So the noisy signal like that. So for example, this is a additive white Gaussian noise process. So the Rayleigh fading channel. So this Rayleigh fading channel we get the noisy signal like this. So in the receiver side model, this is the demodulator of the data. So demodulated data is like a demodulation process of 16-bit QAM near field sequence complementary. So this is the demodulated data of this process in the receiver side process. Similarly, this is the decoder data. Already we see the encoded data in the transmission side model. Similarly to the receiver side model, we get a decoder data. Decoder like data is like inversely to the encoded data. So this is the process of the decoder data of the process. In this figure, this is a PMEPR reduction of the proposed 16 QAM near complementary sequences with MS is equal to 4 and NS is equal to 16. So MS is equal to 4, that is a number of bits symbol. NS is equal to 16, that is a 16 QAM. So that is a NS is equal to 16. So our proposed 16 QAM, this red line. So red line denote the proposed 16 QAM and this is the original OFDM block tanks. So the x-axis is denoted by PMEPR of dB and the y-axis is denoted by complementary cumulative distributed function. So this is the figure of to describe the PMPR reduction of the proposed 16 QAM near complementary sequences with MS is equal to 4 and NS is equal to 16. So finally, the PMEPR reduction of the proposed 64 QAM. Already we before seeing the 16 QAM, their complementary sequences with MS is equal to 4 and NS is equal to 16. So here the 64 QAM we get the results. So in the x-axis we get the PMEPR of dB and the y-axis complementary cumulative distributive function, and black denote the original OFDM plot and blue and red denote the proposed 16 QAMs, that is a 16 type 1 and the proposed 16 QAM, this is a type 2. So compared to this, the PMPR reduction of the proposed 64 QAM, their complementary sequences, it's very reduced compared to this. So these are overall the running procedure for the product. Thank you for listening this video.